Well, hi guys. We're going to have a look at the fascinating land of the logarithmic function today, and I hope that I'll be able to demystify some of the misunderstanding that prevails out there about logarithmic functions and log laws, because it's really very simple. It's just all about indices or exponents. So let's have a go and we'll see where we go. Okay, the logarithmic function first up, the graph of. We're going to look at y equals e to the x, okay, and we're going to discover something very fascinating. There's a relationship between y equals e to the x and y equals log x, and here we go to discover it. So what we're going to do is we're going to take the inverse of y equals e to the x. So in order to do that, you have to swap x and y. That's what you do, my oh my. So you say, okay, the inverse function of y equals e to the x is x equals e to the y. That is it, guys. Now all we've got to do now is make y the subject to get an answer in the form that we are used to. Yeah. Okay. So we take the log of both sides because y is in the exponent. So that's the only way we can sort that out. So we say, okay, let's take the log of e to the y and equate that as equal to the log of x. Now, we're going to take that little y out of on the left-hand side, the exponent term, and sort of shoot that out the front. That's one of the log laws. So we say, therefore, y times log of e with a base of e equals log of x. Now, do you know what the log of e with a base of e is? It equals 1. That's right, it does. So we'll deal with that in a moment. So therefore, y equals log x to the base e. And that tells us that y equals log x is in fact the inverse function of y equals e to the x. They're very close cousins. So, isn't that amazing? So here comes e to the x, first of all, and I'm drawing the line y equals x for you because inverses are always formed by doing a mirror image around about a reflection about the line y equals x. So there's e to the x. It's got an asymptote of, what has it got an asymptote of? Yes, the x-axis, or y equals 0. It's got an index, an intercept, a y-intercept of 0 and 1. Do you see that? Good, because we're now going to draw the inverse. Now, can you just imagine in your mind what you think the inverse might look like? Okay, here it comes. Ready? Can I push play? Here it is. There it is. So y equals e to the x there, and y equals log x there. And it's the mirror image. It is the mirror image, okay? So y equals log x is the inverse function of y equals e to the x, and y equals log x is actually the reflection of y equals e to the x about the line y equals x, as all inverses are formed that way. And thirdly, the x and the y values are swapped, okay? So 0 and 1 is swapped to 1 and 0 for the intercepts. Do you see that? It's amazing, isn't it? And of course the other thing is that this asymptote here, y equals 0, morphs into an asymptote of x equals 0. And of course, the last thing to mention, which isn't written down, is that log is only valid, the domain only works for positive values of x, okay? It's a fussy function. It lives exclusively on a diet of plus x, okay? If you put 0x or minus x into it, you'll give it a heart attack, which we don't want to do that to it. Poor old loggy. So, right, ready to go? It's pretty fascinating, isn't it? It is the inverse function of y equals e to the x, yeah? Okay, here we go over the page. Now, the log laws. First of all, before I do the log laws, I've got to introduce to you the way of thinking about logs when you see them as a mathematical equation. Now, it's really important that you get this, so come on. Have you got a cup of tea? You might want to pause the video and have a look at this very closely, because this is the secret to understanding logs, this page, in my view anyway. Now we're going to say p equals a to the u and q equals a to the v. In other words, p and q are just ordinary old numbers, but they are formed both with a base of a, raising them to an exponent of either u or v for p and q respectively, okay? Right, base is a, in exponents are u or v, the numbers are p or q. Okay, now, remember that the log is just the index. It is just the index. There's nothing mysterious about logs. They're just indices. So if p is a to the u, let's label what we've got here. Okay, that is the number. Say after me, the number. Good. This is the base. That little beastie there is the base. Yes, the base. And that thing there, that u, is called the index or the exponent, but we will call them the index, right? Good. Now, we're going to convert this expression, this very familiar kind of expression, into a very unfamiliar loggy format, okay? So we're going to make the index the subject of our expression, okay? The index instead of the number, which is what you see appearing up there, okay? We're going to make this beast the subject of our equation, right? So we can say that in English is a sentence. We can say that u is the index of the number p with a base of a. Now, do you get that? U is the index of the number p with a base of a. Or we could say that u is the log, because the index is the log of the number p with a base a. Yes? Do you get that? Now we're going to put it into maths now, so come on, stand by, fasten your seatbelts. Writing it as a mathematical expression, or yes, as a mathematical equation in fact, we can say that u is the log of p with a base of a, right? Do you see the way I've done that? U is the log of p with a base of a, and that's how you say it, right? Now I'm going to label those little beasties again. That's the index there, u is the index, okay? That's the base, a is the base, and p is the number, right? Now, I'm going to put the other one that's sitting up there above side by side with this new one so that we can see the equivalence, because it's incredibly important that you know how to just put those little labels on there in cookbook fashion to basically convert from one to the other. That's how you've got it. If you can do that, basically logs just gives up without a fight. It's just easy to do, right? Now, yes, these are equivalent expressions, and it's so important for you to know what is what, which label belongs where in each of those expressions, so you can convert from one to the other. So please learn that. And yes, you have to know how to convert from one to the other. Boy, oh boy, do you ever. Okay, so that's your homework. You've got to know how to do that. All right, over the page we go. Now we will do the log laws. Okay, here we go. The first log law. Now, harking back to our numbers, if p equals a to the u and q equals a to the v, we're just going to think about the indices. What happens to the indices when you multiply these numbers together? Now, you know from your log laws that if you multiply p by q, which happens to be a to the u times a to the b, if the bases are the same, e.g. both bases are a, then what do you do with the indices when you multiply the numbers together, guys? Yes, you add the indices. So, what am I saying here? I'm saying that if you multiply p and q together, you add the indices. So let's just see how we can rewrite that out in a loggy kind of way. So we're saying the index or the exponent, when you multiply p and q together, right, is just u plus v. Aren't we saying that? Yes? Okay? Okay, we're talking about the indices here, okay? It equals to u, which happens to be the index of p, added to v, which happens to be the index of q, doesn't it? So, we're saying the log, which is the index, that I'm rewriting out that expression above in loggy way now, the log of the product of p and q, which is, there it is, I've just circled it, that is what the log of the product of p and q is. It's u plus v, isn't it? It's the index, it's the log. So the log of the product of p and q, which happens to be u plus v, is equal to the log of p, which is u, added to the log of p, q, which is v. So, I'll say it again. The log or the exponent of the result of adding, of multiplying p by q is u plus v, and it's found by just adding the individual exponents, okay, of p and q. So log law number 1 says that the log of the result of multiplying p and q is found by adding the exponents, firstly of p to the exponent of q. That's all it says. Now, come on, that's just a restatement of your index laws. Okay, we're just talking about the indices and what happens to them. Okay, that's it. Here comes log law number 2, which is very similar. It's the dividing one. So if you divide p by q, which happens to be a to the u divided by a to the v, you get the result by your index laws, which you learned in year 10, is a to the u minus v. Yes? So we're saying again, restating what we did above, only for dividing, that the index of the result of dividing p by q happens to be u minus v. And that is u, which is the index of p, subtract v, which is the index of q. So, saying that in a loggy way, the log of the result of the division of p by q, which is u minus v, is found by just taking the log of p, which is u, and subtracting the log of q, which is v. Okay, so here comes the log law. The log law number 2 states that the index or the exponent of the result of division of p by q is just found by taking the exponent of p and subtracting the exponent of q. That's it. Now, come on, that's not very hard, is it, when you think of it in terms of just your index laws? No, that's all it is, okay? So that's what all this mumbo-jumbo log stuff is all about, guys. Here comes another one now, while we're on a roll. This is number 3. This is when you raise something to a power. So we're saying that, yes, we're saying p is a to the u and q is a to the v. What happens if we raise p to a power, say, to the m? Well, that really means p to the m is a to the u to the m, doesn't it? Which, according to your index laws, you know, don't you, that equals a to the u times m, doesn't it? Well, that's what this log law is about. Let's go for it. So we're saying that the index or the exponent of the result of raising p to the mth power is u times m. There it is, right? Now we know that the index of just p, which happens to be a to the u, is just simply u, isn't it? Yes, it is. So therefore, what are we saying? That the log of p to the m, yes, that's the index, which is the log, okay, it's equal to u times m, and we're saying that the log of p, which happens to be a to the u, is also u. So therefore, what are we saying as a result of all this? We're saying the log of p to the m, which happens to be the index of p to the m, which is u times m, is equal to m times the log of p, which happens to be u, right? Yeah, okay, so if you're taking p to the m, yes, you just basically multiply the index of p by the m, right? That's what you do. That's what the log law says. So here it comes. Log of p to the m is just m times the log of p. That's it, right? That's it. That's log law number 3. Okay, log law number 4. Now this is an easy one. This is just the log of 1 equals 0. Anyway, we'll go for it. P is a to the u, and u, therefore, if you rewrite that in the way that I showed you at the start of this log law stuff, if you rewrite it into the other form, the equivalent expression form where the index is made the subject, you're saying that u is the log of the number p with a base a. Yeah. Now, what happens if u was 0, guys? You'd know that p would be a to the 0. And what's a to the 0? Shout it out at me. Yes, it's 1, isn't it? Of course it is. Anything to the 0 is 1. So if we rewrite that in our loggy format, we're saying that, yes, if u is log of p with a base a, that becomes, the u has been made 0. So 0 is log of 1 to the base a. Yeah. In fact, that's the log law. That's log law number 4, which says that log of 1 equals 0. Log of 1 to any base equals 0. So I haven't written the base in there. Log of 1 equals 0 for any base. So if you say that to yourself 50 times, you'll remember it forever. Okay. Log of 1, any base, equals 0, right? Good. Right, my goodness, there's the log laws. Now we've got to use the log laws now. Here comes an example of how we use them. So, what have we got to do? We've got to simplify without using a calculator the following. Well, that looks pretty disgusting, but look, never fear. It is really easy. Now we're just going to go backwards with those log laws. We're going to go backwards, okay? We're going to simplify them. I think the first thing I might do, well, come on, have a look at it. You think, what would you do first? Well, I think, look, see this pesky looking 3 here? You've just got to get it so it's log something without, you know, these coefficients in the front. So we're going to turn that, take that 3 there and put it up there as 3 to the power 3, or 3 cubed for a start. That'll help us. And this little beastie over here, that 2, we're going to get him out of there. So it's just saying log instead of 2 logs. So that'll be the log of 6 over 5 squared. Now, okay, now which log law was that? That was log law 3, wasn't it? Yes, when you're raising something to a power. So we're going backwards. And we'll write that out first. There it is. Okay, good. Now we're going to do log law 1 and 2. And we're saying that if this log is added to that log, that must mean that that is the index of this number multiplied by that number, okay? And then this here is a dividing one because it's a subtraction one. That's log law number 2. So really this is telling you that if we've got the log of this plus the log of this minus the log of that, it's telling you it's the log of this number multiplied by this number and divided by this number. That's what we're saying. We're talking about indices here, guys. The index laws. Right, hope I'm not driving you crazy with all this repetition, but it is important. So there it is. There it is. There it is. Now, I think that little beastie there is a bit of a problem. We'll just flip him because we're dividing by a fraction. And you invert and multiply, don't you, when you're dividing by a fraction? So fix that up. Good, now we've got to simplify this mess. Well, that's 27 times 16 over 3 times 25 over 36. Now that's interesting, isn't it? Because this 3 goes into that 9 times, 9 goes into 36 4 times, 4 goes into 16 4 times, and 4 times 25 is 100. My goodness. Look at that. Now, look, you see I'm excited because look, see this here? We've got a base 10 and the number we're looking at is 10 squared. Well, come on. What is the index? The index is 2 and the index is the log, isn't it? Of course it is. So the answer is 2. For me and you, woohoo. There it is. There's the answer, right? You get it? Come on, it's easy. Now we'll do something else now. We're going to logarithmic equations. Oh, yes. These come up all the time, these things, and they're full of booby traps, so beware. I'm going to show you how to not fall into the pit and get it wrong. Now, okay, can you see that's an equation? It's got an equal sign there. Now, okay, so what we're going to do is we'll just merrily go along and solve it first, and then I'll show you the booby trap, yeah? Now, right, so in reverse, we need this 2 out of here. Okay, so it's got to be log of x squared. Anything else? No. All right, so, and then we can do our log law 1 and 2 after that. So this is dividing this one. So let's go and see what we do. Yeah, good. Okay, yes, agree with that? Yeah, yes, good. Now, if you've got log of something equals log of something else on the right-hand side, it just means that the things behind the log signs must have been the same. You know, if the logs are equal, the numbers must have been the same. So therefore, we can just dispense with the log terms now. And we get that, which is really easy now, isn't it? So come on, cross multiply. Yes, yes. Oh, it's going to be nice and easy to solve. Quadratic, okay? So get it all over equal to 0, like that. And I think it's going to be easy, yeah. 2 and 1 on the left factors and 3 and 1 on the right-hand factors, and I think it works out really nicely. Good. Therefore now, this is where the danger comes. Do you see that? Do you see that? Now, this is where when you do these logarithmic equations, you must go back. Must go back and look at the original equation here. Because, look, whatever's in here behind the log sign must be positive. It must be positive, otherwise you blow the log up and give it a heart attack, which we don't want to do that to the poor thing. So therefore that x has to be positive, yes? And the x plus 3 here has to be positive. So what's that telling you? Okay, x is greater than 0 for this, x is greater than -3 for this one, isn't it? Right, so they will both be covered nicely if you just say x is greater than 0. So x must be greater than 0, guys. Otherwise you'll blow the log up and give them a heart attack. And if you look down here, look at that. Look at that. Ooh, that was a near thing. We almost had to call the ambulance. See? X can't be negative. It's not allowed to be negative. It comes out because you're just solving a quadratic. But look, if you look at the context of the question, that won't work for this particular context, right? So you have to reject that solution, and that's the thing that students forget to do. That's the booby trap, okay? So here it comes. I've written it all out here for you in red, so you won't forget it. You can't have the log of a negative number. Oh, no, 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 you cannot, okay? So in the equation above, we know that, there's the equation above, we know that firstly, that has to be greater than 0, and that has to be greater than 0, which means that x has got to be greater than -3 for that second term. So they will both be covered amply if we just say, therefore, x has to be, the more restrictive one is x has to be, if we say x is greater than 0, then we've covered both of them, haven't we? Yes. So there it is, that covers both, yes? So therefore we have to reject the x is -1 solution, and we say therefore that is the answer. X is 3 on 2, guys. Now, that's really important. I hope you got that, okay? You've got to watch, because they'll throw them at you. And you can't fall into the pit, okay? And send the poor old log function to hospital. Now, log graphs. We're going to do some transformation throughout the nation. Yes, yes, I heard you sigh. I'm sorry to do this to you, but hey, it's not that hard. I'll show you the patented Wolfie way of doing this, okay? First of all, we're going to do A, and we're going to start off with the standard, we're going to compare this to the standard graph of y equals log x, and you'll notice that I've put some dashes in here, because this is the transformed function, y dash x dash, compared to my original one of y equals log x. Now I've got to work out what happened to y equals log x to get to that transformed version. And this is the way I do them, right? That's the transformed one, that's the original one, yeah? Now, okay, so you've got to put the transformed equation in what I call equivalent form. Equivalent form so that you then can equate the y dashes with the y's and the x dashes with the x's. Now, that means you can't have any stray or orphan, as I call them, terms. Now, what does that mean, Mr. Wolfman? Well, don't worry about it. Look, I'll show you. Every number, every numeral, okay, like the 3's and the 2's here, not the pronumerals, but the numerals, they have to be attached, very firmly welded onto it, either an x or a y term. Now, this 3 is welded onto that x term. It belongs to the x term, right? But this 2 is just sitting out here. He's not specifically stuck onto the x term. So therefore, really, he doesn't belong there. He belongs to the y term. All these numerals have to be attached to a y or an x by either a direct addition or subtraction from the x or the y term, or by a multiplication or a division of the x or the y term. That's what they have to be doing. If they're just sitting out here, swanning around here, stuck out in front of a log term or a sine term or something like that, they don't belong there in terms of the fact that, in terms of thinking of them as orphan terms. They're orphaned. They need to go back to mummy or daddy, to home base. Yes? So really, if you rewrite that out in equivalent form, it'll be like that. Right? Now, I've got my two equations. They're in equivalent form, and I can just sort of read them off by equating them, the y dashes with the y's and the x dashes with the x's, right? Equating 1 and 2, that's it, and therefore y dash is 2y, and therefore for the x I've got that thing there, 3x dash equals x, therefore x dash is x over 3, isn't it? Now that tells you exactly, ladies and gentlemen, what is happening. To get to y dash from y, you've got to multiply the y by 2. To get to x dash from x, you've got to divide the x by 3. These are dilations. It's very, very plain to see. Okay? So, what does that mean? It is, that one is a dilation. It's a factor of 2. It's a y dilation, a y stretch by a factor of 2. But which axis is it stretched away from? Yes, that's it, but you actually have to refer to the other axis and confuse everybody. But you first of all get your head straight that it is a y stretch or a y dilation. That's what it is, right? Okay, now this one here is a dilation. Well, in fact, it's a compression. Everything is squashing into a third of its normal size. It is an x compression, but you call it a dilation of a factor of a third, but meaning the same thing. And it's an x stretch or compression, but which axis is it in reference to? You say it is from, yeah, you say it's from the y-axis, but you've got to get into your head that it's an x stretch, right? Okay, let's go over the page and do it. My, this is fun. All right, I heard you. Don't be rude. Now, here we go. Here we are. There's base. That's home base. That's y equals log x. Yeah. Now we're going to do the transformed one. Here it is, guys. Now, what did I do to it? First of all, the compression, the x compression by a factor of 3 means that x-intercept goes down to a third instead of 1. Yes. And in order to show the stretch of a factor of 2, we'll just take a reference point, and 1 would be a convenient point to take. So what would that do? Yeah, that would get us to, when x is 1, that would give us log of 3, and then it's times 2, which would get us 2 log 3 up there on the y-axis. So both of our dilations are being shown very nicely. Yes? There she be, guys. You like it? It's beautiful, isn't it? A work of art. Right, here comes B for you and me, and then we'll be finished. This one here, looks like a nasty customer, doesn't it? But fear not, we'll use our Wolfie technique here. It's very, very foolproof. So we've got y dash now, because this is a transformed function, remember, compared to y equals log x. Yes, here it comes. Now, same old, same old. Now, are they in equivalent form? You ask yourself, are they in equivalent form? The answer is no, they are not. Because this little beastie here is a numeral, even though he's not looking like a numeral, he's a -1. And he's not welded by a plus or a minus or a dividing or a multiplying to any particular term. He's just sitting out there, escaped from where he belongs, outside the log term there. So we're going to divide both sides by -1. That's what we're going to do. And what do we get? That's what we get. Now it's in equivalent form. Now it's in equivalent form. Okay, there's our two equations. Now we can just equate them. We can say that. What can we say? Yeah, we can say this. We can say that, and we can say that. Yes, can't we? Therefore, making y dash the subject and making x dash the subject. Now, okay, it's very easy to see what's happened now. That is a reflection, okay, about the x-axis. So y dashed is minus y, so it's reflected around the x-axis, hasn't it? And x dashed is minus x, which means it's reflected mirror image around the y-axis, isn't it? Think about it. Come on, in your head, think about it. That's what it is. Okay, so we've actually got two reflections here. That's what we've got. I think we're going over the page to finish it off. Oh, wow, nearly there, guys. I'll just hurry this up a bit. There's home base. There's y equals log x now. You happy with that? All right, now I'm going to do the reflections one at a time, okay? This one here is reflecting. That's okay. What was up is now down, and what was down is now up, if you like, in terms of negatives and positives. So I've reflected it about which axis? The x-axis, haven't I? Now I'm going to reflect it about the y-axis now. Come on now, visualise in your head what you think it's going to look like. Come on. You ready? Okay, let's go. There it is. Okay. Now I've reflected that about the y-axis, so that's it. So that is our new transformed function, which is y equals minus the log of minus x with a base of e. Whoopee! My goodness! That was amazing stuff, wasn't it? Yes, and it's thumbs up to everybody. Now I'm sure you got that. If you had any points of confusion, just go back and have a look at it and you'll be fine. And we'll see you next time. And thanks for watching, and have a wonderful day.